All right, now that we're learning to take derivatives of usual algebraic expressions, our next topic is derivatives of exponents and logarithms. So what's the derivative of the function 2 to the x? You could sketch it on paper. It's not a bad plan. So what would we say? Over here, the tangent lines have a positive but shallow slope. Over here, the tangent lines have a positive but stronger slope. So overall, it should have kind of an upswoop. It's not clear whether it'll be above or below, but if you go try it in Desmos, you'll see something like this. But Desmos doesn't give us a formula, but we can see it has the same basic shape, but is a little bit smaller. If you do the same thing with f equals 10 to the x, you get, again, the same logic applies, but this time the derivative is higher than the original function. So a good question is, so here's a 2 to the x, here's a 10 to the x. Is there anything I can do that will give me a derivative that's exactly the same as the function I put in? So I want you to switch to Desmos right now and play around with it, and then I'll switch to Desmos and we'll see if I end up with the same thing you ended up with. All right, welcome back from trying it on your own in Desmos, and let's see what I come up with here. So I had said that if we do f prime, and I'll turn that to red, we end up with f prime for 2 to the x is the same basic shape as 2 to the x, but as a little lower. And if I tried 10 here, then f prime is larger than 10 to the x. So what number would give us derivatives that's the same between the two? Anytime you find yourself playing with numbers, like I could go back and change this to like a 3 or a 4 or something, but you can just make it a slider. I'm going to call it b because it's a base. And now if I change b, I have all kinds of fun. So we know at b equals 2, the red curve is below the blue curve. The derivative is below the main function. At b equals 10, the red curve was above. What do I have to set b to get them to be roughly the same? Somewhere like 2.3, the red curve is the derivative is above the blue curve. At 2.6, the red curve is below the blue curve. So somewhere between 2.6 and 3, 2.7 is looking pretty good there. But I could plot f prime of x minus f of x to see if they're the same. If they were the same, I would get all zeros here, but I'm not getting all zeros. I need some better resolution on this slider. I know it's somewhere between 2 and 3. So what can I do? 2.72 is too large. 2.716 is too small. So I could go 2.71 to 2.8 maybe. I know it could have been a little bit better on that, but if I do that, okay, so it's 2.718. Is 2.718 sounding familiar? Well, remember E is 2.7182818, blah, blah, blah. I should have that memorized in more places, don't you think? So anyway, it looks like e to the x is the function whose derivative equals itself. So that's why that's one of the reasons we love e so much. So let's go back and look at that on paper. All right, so we found that if we have f equals e to the x, then the derivative falls right on the function itself. Pretend I stayed on the line there. So we can summarize that by saying e to the x prime, the derivative of e to the x, is e to the x. This brings up the question, what is the derivative of 2 to the x? It seemed like it was 2 to the x, but with some multiplying factor, some vertical scaling factor. And you could go play with it in Desmos, like plot 2 to the x prime divided by 2 to the x and see what you get. And you'll basically find out that the derivative of a to the x is a to the x times log of a. Okay, so we usually don't use a to the x, we just use 2 to the x, just use e to the x. So that's for exponentials. This one is very, very important. This one is not so important. Let's talk about logs. So let's draw log here. Looks like that. And let's think about its derivative. Well, here, you know what I'm going to say, right? I have a positive but not very strong slope. So go do all that and then come back. So I have a positive but not very strong value here. Here I have a positive and stronger slope, so I have a positive and stronger value. And over here I have a positive and very strong value, a positive and very strong slope. So I'm getting a curve kind of like that. And the slope is always positive, so this is going to tail off but never quite get to 0. And this was actually in the demonstration I did for the Chapter 99.1 homework. So it has all positive slope. So here it has all positive values. Let's try that again. And we asked, what is this shape? Is it e to the negative x? Is it minus log x? If it was e to the negative x, what would that look like? It would look like that, so that's a good start. But e to the negative x crosses the axis here. So it has a finite value at x equals 0. But this slope is getting steeper and steeper, and log can never touch 0. It doesn't actually have a slope at 0. So this can't match the derivative of log. Someone else once said, is this negative log? Well, let's graph negative log. It's just like log, but upside down. So it does that. So it ends up being negative over here, but we know that this has to stay positive. So this shape is not e to the negative x, and it's not negative log. What it is actually, and it's almost impossible to figure this out just from knowing about log, the derivative is actually 1 over x, or you could say it's x to the negative 1. And we'll see that later in class, later in the semester as well. All right, so let's write that again. Log x derivative is 1 over x, and that's a natural log. There's another formula for the log based something else, but we basically never use that, so I'm not going to stress about it. You can go look it up if you need it.